All right, we're going. So PPO-Clip is it's an Actor-Critic method. This is what you can see on the camera. Looks like everything. PPO-Clip. So there's two kinds of PPO algorithm. They are both based on this TRPO algorithm that came before, which is called trust region policy optimization. PPO-Clip is the one everybody uses, and then there's another one called PPO-Penalty. Nobody uses it. So the algorithm goes like this. Do you put this for audio? Yeah. This should be okay for audio. No. Like, it's not super terrible. There's no interference. It's just like when people scream over there. I'll have to synchronize it if I use two devices too. So you have two inputs to the algorithm. The first is you have, let me go over the layout first. So because it's Actor-Critic, you have to have two neural networks. You have one which is a controller network, which is the policy network. So the policy network is something that takes the state and that maps over here to the neural network, which is the policy network. That outputs some action. And this has parameters theta. Okay, so those are the weights. And you've also got the value network, which is the state. So this is the value network again. And really, this outputs a distribution of action probabilities. So action probability distribution. Okay. And this is like if you have ST or just S, lowercase s, then this will be it'll be a vector where you have S and then a particular action. And so this pi is parameterized by theta. And this is just a number between 0 and 1. And basically you plug in a state and an action you could take in that state, and it tells you the probability of that. So that's the notation you use for that. Here the states are S, and you have parameters phi. Same thing as theta, just a different label. This is the value network, so it should output an expected return over the rest of the episode. And this is denoted V sub phi of state. And this should be all action states for S. So this is the setup. You need these two things. When you are actually running your algorithm in control for the rocket, you won't have this anymore. This goes away. There's some like reinforcement learning control schemes where you keep this in the real-time environment, but here you don't. So we're just trying to get a good policy network, and the value network is used to help it update. So you have two inputs to this algorithm. You have the initial weights for the policy network, and you also have the initial weights for the value network. And you use some kind of like smart random initialization algorithm for that, like Xavier or initialization. The algorithm goes this way. Now run a loop, and K is going to be, it's not really tied to anything like it was in reinforce. In reinforce, you actually had K being the number of epochs or the number of episodes that you've run so far. But in this case, you don't. So the reason why you don't is because the first step of this for loop is that you run some trajectories. and store them in a set called dk. And it's a set of trajectories, and we denote each trajectory by tau sub I. And these are ran with whatever the current policy is. So the way we say that is Ti is sampled from the trajectory space with the, is it pi sub I? Pi sub theta sub k. So if you're at k equals 0, you just run it with the initial policy parameters, and you just run a trajectory, which is an episode. And then you store that in here, and then you keep doing that until you're satisfied. However many trajectories you want to run, doesn't matter.
And you were saying that value network is kept aside during the episode?
Yeah, so here it's not getting used. We'll actually use it in this for loop, but this is only for training the policy network and the value network. Once you actually get done with this for loop, and then you go to deploy in the real world, you won't have this anymore, and it's not used. So really the ultimate goal here is to learn these thetas, but we'll actually have to do some stuff to learn these on the way. Now, the next step is we want to calculate the rewards to go. So you have to save some stuff when you do these trajectories. You got to save your actions. And I write A sub t super I to denote the I corresponds to the trajectory that you're running. So if I is 1, that's the first trajectory you do for this k. And the t is the time step, so you have to save an action for every time step. And you also need to save the rewards that you observe every time step, and you have to save the states that you traverse at every time step. The way to remember these three, because like after a year of not doing reinforcement learning, you'll kind of forget, is there was an algorithm that was kind of famous called SARSA. And this literally means state, action, reward, state, action. So that's all that's involved in saving stuff. And I won't write this, but just keep the I out there. But if you want to, you can. So next, you calculate the rewards to go. So these are called R hat sub t super I. Again, we won't write that. So what this is R hat sub t is the sum. What do we want to do? We want a letter like T, but not exactly T. So we'll say alpha equals T to the end of the episode, capital T. And you just sum up all the rewards. Okay. You can also put like a number here, lambda, which is less than 1, and then take it to the power alpha if you want to do a discounted rewards to go, but you don't have to. Okay. So that's how you calculate this. You just calculate those for every time step in every episode. It's just the sum of all the remaining rewards. Okay. Now step 3 is estimate the advantage function. A hat T. So what does this consist of? So what is the advantage function, firstly? So in some sense, like, you're running this policy that you got from your parameters theta sub k, and you don't know if that policy is optimal. So there might be a better policy, and at every time step, you can possibly have like a different action than the one you actually did choose that would have given you a better return overall, obviously. So the advantage function is a way of saying, let's see, it's a way of capturing the difference between your policy and the best policy in terms of the returns you can expect. So what this is formally, this isn't for your actual parameters you get. It's like assuming you get like the optimal policy or whatever. The advantage, so I'm writing pi star to denote the optimal policy, which is if you knew the best move to take at all times, that's what this policy is. It just takes the best move every time. Maximizes reward. And you plug in a state and an action. And this is equal to the Q function for that optimal policy. Or I should say the optimal Q function, actually. Minus the optimal value function of the current state. So what is this? So the Q function says, let's say I'm playing a game and I have a current state and I have a bunch of different actions I can take. You can imagine that I picked out the first one of those possible actions and I take it, then my reward I can expect after that is a certain number. And that's what this is. So you pick out a state and you also pick out an action you could take in that state. And then you say, what is the expected return after taking that action? And that's what the optimal Q function is. Assuming that the rest of my moves throughout the rest of the game are perfect. Now, there can be stochasticity in how the dynamics of the states evolve as you take actions. Like, you can't predict what will happen after you do a certain action. But as long as you play perfectly, knowing that things are probabilistic, then Q star is what that is. It's the expected return. So in tic-tac-toe, I can't know if you're going to play like really bad or if you're going to play perfect for a draw every time or whatever. So I just got to play assuming worst case. And this will be the maximum return I can expect after taking action A. The value function is almost the same thing. It just says, what is the expected return from right now without actually taking any actions, assuming I take the best action right now. So this is like A is maybe a suboptimal action. V is assuming this is like equal to Q star S A star, where A star is the best action you can take right now. So that's what it is. So this is trying to capture how far away from being the perfect action is this action that you've specified that you want to check. That's what the advantage function is. So a nice way to estimate that is, here's a picture. With the value network that you've computed, I had somewhere I had written it down. Let's see. So there's different algorithms for doing this, and the one that they suggest in OpenAI's documentation is to use the generalized advantage estimation lambda algorithm. Because you can't actually compute Q star and V star. Like, you don't know what the optimal policy is. You don't know what the optimal value function is. So you're going to estimate this thing. And what that ends up being is A hat T. Hat means it's just it's some kind of estimate of the advantage function. It's R. Where is it? R sub T lambda minus V sub V of ST. So this r sub t lambda is the same as before, but with discounting. So they suggest you actually do discounting. You can just do this if you want to. But they find you get better performance if you do discounting. So that's the idea. You could just write this if you wanted to. So that's the advantage function estimation.
Do you also want to remove lambda from there?
Where?
GAE.
Here? No, I'm just assuming it's part of this, like when you do the original calculation. Yeah, this would be like GAE 0 or something, or GAE 1 if you didn't use lambdas here. So I just write 1 instead of lambda. But yeah, you actually use lambda discounting here. I think you can, instead of doing that, you can actually calculate these rewards to go, and then when you plug in your RT here, you will you can, like, there's a paper about this, so you can just check and be sure, but you could probably just like stub in a lambda to the power of t or something.
Oh, I think I've seen something like that.
Right. Yeah, this is how discounting goes in general, but yeah, it's not terribly complicated. You just got to check the paper when you're actually programming it. Okay, so now there's 2 more pieces to this algorithm, and these are the fun parts because they actually update your parameters for your networks. So for updating, we want to update this guy to get theta k plus 1. Okay, so how do you do this? All right, so I need the algorithm here. So you want to maximize. So you want to set this as close as you can to the right-hand side of this approximate equality. And it is this argmax theta. So imagine all the policies, all the policy parameters you can have, and then take the one that gives you the highest, whatever, on about the right. And then you average over the total amount of episodes that you ran times t, which is the length of an episode. And here we're kind of assuming that the length is constant, so all episodes are the same length, but you can adapt this to be variable length if you want to very easily. And then you've got sum over tau in dk, so all the episodes. So again, we're averaging over the episodes here. And then you average over all the time steps. T equals 0 to t for that episode. And then you minimize. I'm going to run out of space here probably, but yeah. So let me put this sum in down on a new line. So you minimize the following. Pi sub theta AT given ST over pi sub theta K AT given ST, and then the advantage function A theta pi theta sub K STAT G, is this G epsilon? So I'll put that on a new line. G epsilon. Ugly. A pi theta k SGAT. I think that's right. Yes. Okay. So you want to maximize this average. Okay. And these, the advantage functions, are precisely, well, they're not precisely, but they're estimated by the a-hats. So what you're doing here is these pi sub theta k is, these are your current policy network parameters. And so you're actually running the state that you're currently at. You'll go over every state that you saw along the trajectory, and you'll plug that state into the policy network. And then you'll just look at the action that you actually took. And then you'll compare that to some candidate output from the policy network after you had updated the weights. And so the way you actually do this update is, how do you find the argmax? Like, how do you find the policy weights that give you this thing? Well, you do this with SGD, with Atom. So you just do gradient descent, use your favorite optimizer for that, like Atom or something, and it will find a good theta. And I was looking to see when you stop that, because this is per set of trajectories, and then you'll rerun and get new trajectories and do the same thing again. And they put a finite cap on the number of gradient descent updates you can do in this step. And then they also have a Kullback-Leibler divergence check to do early stopping in case you get, because in PPO you don't want to do a huge update on your weights every step. You want to cap that, and that's kind of what guarantees that you're going to have stable policies. So they do this
analogous to the learning rate.
It is not. So the learning rate, in a way, because learning rate being small guarantees that you're close to the true gradient flow, and you don't jump off and then get somewhere where the vector field doesn't look like it originally did. So that's kind of the idea. Yeah. But the way they actually measure difference is with this Kullback-Leibler divergence, which is kind of like a distance for probability distributions. And this, the pi's are like a conditional probability distribution, so to speak. And so you can measure the difference between pi with theta k and pi with some candidate theta using Kullback-Leibler. And there's a way to calculate that explicitly. And I think like SciPy will have something to do that if you want to implement this manually. So what else is there here? I feel like we're missing something here that makes it not clear. So how do you actually go about making this stochastic gradient descent update? So you want to update theta to maximize this thing.
Before we go into this, I have a question. When you're running this for different Ks, like the outermost loop, do you throw away previous trajectories or stay like?
You do, yeah. Yeah, you don't keep them. So later on after PPO, DeepMind came up with DQ networks, and that is, I can't remember if it's Actor-Critic or not, but they save a replay buffer, and it's basically they save conditions or observations that defied whatever the value function or the Q network thought was going to happen. And so it keeps stuff that is like unexpected, and it trains on it more over time. And then it throws away things that are irrelevant.
Or that is being repeated.
Yeah, things that it understands well, it throws away. Like things that it can predict accurately. But that is more expensive. You have to save memory. It's good for like online learning because you can do it while your rocket's flying or something, and it'll remember what happened. But PPO works also online, and it's cheaper, easier to understand and write. So to actually do this stochastic gradient descent update, you want to maximize this thing by changing theta. And so what you want to do is you want to calculate the gradient of this expression with respect to this theta. That's the only place theta shows up in this whole thing. I know it shows up here, but that's a different thing. That's your current weights, which you don't update. You actually want to calculate the gradient of this whole expression with respect to that thing. And then multiply that with the learning rate parameter and step in the positive direction of that. Okay? Just update this in the positive direction. You'll have a learning rate. The learning rate doesn't matter so much because you're probably going to use Atom. It's going to have an adaptive step size solver. Momentum and stuff. Probably like 3e negative 4 usually is what I use for Atom. Okay. So that is the policy network update. This does all the work in training your policy network. Now, you want to update your value network's parameters. Is it theta or v k plus 1? So how do we get that? This should be. Do this in here.
So just to be clear, so this is happening. The weights update are happening for a bunch of episodes. Like you do this only once after a bunch of episodes.
So you saved your episodes, however many. I ranges through 1 through n or something. You then average over all your episodes, and you average for each episode over the time steps. And for this thing, you run this one time. And then you'll get some new episodes to train over, and then you'll run the whole thing.
And when you were saying that for a PPO, we only need like 100,000 episodes, right. Was that this outermost loop or the inner? Or these trajectories?
Episodes.
Okay, so you're talking about trajectories.
Much cheaper, like 60 times as cheap as Read Force. It's really good. And like doing the update is much cheaper than actually running the episodes.
Right, it is.
Because you have weight.
Maybe depending upon if you're running like a small ass game, it should not be expensive.
That's true. Because you do have to do it over every time step.
And depending upon like how big your policy network is, it's going to be pretty expensive. How many times you think this Atom, like this SGD is optimized? How many weight updates you think it's spent?
So there are two places you can check. There's the spinning up documentation from OpenAI, and they have an example implementation of this, and they show you the default value. So that is, let's see, it says it right here if I can figure out where it says it.
You said spinning up?
Yeah, spinning up, OpenAI. So they do each one. They do this gradient descent, 80 at most, 80 steps.
80 steps?
Yep. And they do this one, 80 at most. By default. You can change it, but that's what they default
in
to.
In the moon landing example? Or?
Just in general. They don't do it on any environment. They're just showing you what the algorithm is. But I would start there and then tune it based on whatever improves performance. And then they also have early stopping with callback live load divergence. So when I say SGD Atom, I'm saying SGD Atom with early stopping based on callback live load divergence between theta and theta sub k, these two guys. So you can, after you do an update, or after you do like 5 updates or something, you'll check the callback live load divergence between them, and if it exceeds some value like 0.01 or 0.05, you'll stop.
How is that defined?
Just any statistics textbook will have an explanation.
You said some sort of distance is going on, right?
Yeah. It's not exactly a distance, like it's not technically a metric function. But yeah, it's like a distance between probability distributions. And your probability distributions of these guys. But like NumPy or SciPy or something will have it implemented already. So just plug it in. Okay. So now for the value function update, you want to do the same kind of thing, but now instead of maximizing, you're minimizing. So you want this to be approximately the argmin overall phi of 1 over, we're going to average again, dk t, and you're going to take the same sums, tau and dk, sum, this is going to be t equals 0 through t, and this time it's just going to be the mean squared error of the given to you by the advantage estimate. Is that right? Yes, that's right. So that's going to be v, and they write it backwards for some reason, but I'll just do what they do. Minus r hat t squared. And that's it. You just do gradient descent on this. And same parameters. I think you do early stopping with go back library. I think.
Is that why you call it PPO-Clip?
It is because of this thing, this minimum. This. I didn't really explain what this G function is, though. We'll look at it in a second after I get done. This epsilon is something you pick as a clipping parameter. It's some small number that measures the.
Oh, yeah. You're right.
It tries to make you not do large updates. Even if your advantage is huge, which means you could improve your policy a lot. It's like a regularization tactic. Okay. So is that it? That's it. So N4, and we're done. So after you run this for a while, you have a trained neural network for your policy network. So all there is to answer at this point is what's this G function thing here? So what is that? So again, epsilon is how far away from the new policy the old policy can be in terms of the advantage. So it's not like a Kovac-Labler distance where you want to constrain how far you can actually change the parameter or the outputs from your neural network. It's actually a distance in terms of reward. So it's kind of the principle where like if somebody comes up to you and offers you like $1 billion for like flipping a coin or something, like you wouldn't take. I mean, if there's any risk at all to you, you wouldn't take it because you're obviously scamming. So the idea is like if your advantage is too huge, you don't want to. It's probably like some kind of indication that your value function is spitting out nonsense.
Maybe reward hacking.
Not reward hacking, because that can actually give you high rewards. So this will actually not help you. Like PPO will still have really bad reward hacking properties.
I mean, it could be reward hacking gave you that big of an advantage, right? In the
No, this won't. Yeah, but you'll still, if you find a good reward hacking policy, you'll still learn through successive updates to keep exploiting it. But because this is kind of like a regularization, you'll act on things that are less sparse. And so if it's like a frame perfect jump or something, like in like a Mario speedrun or something, you will be less likely to exploit that over just actually playing good. But you'll eventually learn to exploit it if you keep trying. So, okay, so this is actually defined explicitly. So I'm gonna change the inputs here. So A, just any old number A, and some small epsilon that's positive. This is going to be defined as a piecewise function of of A. So it's 1 plus epsilon A if A is greater or equal to 0, non-negative, and otherwise it's 1 minus epsilon. If A is negative. That's it. That's all there is. So you'll just you will differentiate this whole thing with respect to your theta, and you might think, okay, well, are there any other hidden thetas anywhere in here that I need to differentiate with respect to? And there aren't, because the only thing kind of funny that shows up is a hat t, which is just this, and it does have parameters, but it's not theta. It's your value network parameters. So you don't have to worry about it with this gradient.
Right.
So this is very easy to figure out how to do the gradient for. If you have an auto-grad library like in JAX or whatever, this will be straightforward. That's it.
It was manageable.
Yeah. Yep. Not too many hyperparameters or anything.
Yeah.
But this will have a learning rate. It'll have a maximum number of iterates you can do for your gradient descent, and it'll have an early stopping threshold for your Kullback-Leibler divergence. And then this will have all those three things as well. Maybe no. So, yeah, the epsilon. Yep. So there's 4 for that.
Yep.
And there should be just 2 for this. I don't think you do the early stopping. So just your learning rate and how many iterates to run this for.
Why don't you do early stopping?
You don't have a probability distribution to compare to. So Kullback-Leibler, you're doing it's distance for probability distributions.
But you said there's still a hard-coded limit, like 80 steps?
Yeah.
Like that. And is the early stopping logic like this, that if at any step the difference or whatever that metric is too big, then you just stop, break down the
Yes, that's right.
situation.
You don't do anything funny if it gets above. Like, it's just that. Yeah, some people just call it KL divergence. Okay, so yeah, this definitely does not have early stopping. So it always runs for 80 or whatever number.
And these two update steps are completely decoupled, right?
Let's see. Yep, because everything here is already saved before, and it doesn't depend on whatever theta is. It did when you actually got the states or where it goes, or wants to go, but they're pre-calculated up here, and by the time you update this, it doesn't affect anything you saved. But yeah, important thing is you actually got to square this difference. So, I think you can take the absolute value and it works fine, but it probably will be slower to converge or less stable or something.
Maybe faster to converge. I don't know if that value will be bigger than
MSCs typically. No, I'm saying the algorithm will converge to a good policy faster. This number, this is finite, so it always converges. Maybe smaller, probably, but.
For the policy, does that ratio just convert to just the LM?
No. Let's see. No, this is a constant on the bottom with respect to theta. I know it says theta k, but that's just a pre-saved parameters. So you can actually pull this out.
Not from the minimum though.
No, you right now here.
And what does it mean by taking? Yeah, what does it mean by taking the minimum? If we're like taking the average, if we're summing up all of the entries.
So no, for each summand, if you fix a particular trajectory you're looking at, you fix a particular time step, then you look at the minimum of these two quantities for those fixed trajectories and time steps. And when you do the gradient update, it's going to be kind of funny because how you take the gradient of the minimum. But you can imagine, let's look at ReLU. ReLU is defined. I'm just thinking of that because it's like an easy to define function in terms of minimum or maximum. ReLU is f of x equals max of 0 and x. So if I wanted to know how to take the derivative of this, how would you do that? Can I just do the derivative of this and the derivative of this? This would be 1 and 0. Does that work? No. Right.
You have to break it into a piecewise function first.
So you look at ReLU, looks like that. So if you're over here, that's when 0 is bigger than x, so your x is negative. So you'll just have 0 for your output then. This is f, this is x. And so the derivative should be 1 on the right side. Here, the max of these two is always 1, so that wouldn't work. So you can't just put the derivative operator inside the maximum. You can make it piecewise and then just check where you are. Which one of these expressions you're using? Let's see.
I think computationally that's the only way, right?
So I think AutoGrad libraries will automatically do the check for you, so you don't actually have to save anything, like figure out which one's minimum. Yeah, I think it is. You have to literally calculate these values and then figure out which expression is the one that is the minimum. And then once you know which one, you can differentiate that one.
Does that needs to be done at every iteration of this weights update step?
Yes, but the nice thing is that this is always 0 derivative with respect to theta.
Yeah.
So you just, and it's easy to calculate.
Yeah, it is.
So you end up only having 0 or whatever the derivative of this thing is.
And you have to compare this value at every time step?
Yes, that's right. Yep. This one's cheap.
And this one's cheap. You can just save it for money.
Well, I mean, it's this guy. Very, very cheap. You can't save it because you only end up using it one time, though.
Like you can compute this before like doing the descent. For
that's true. That's true. Yeah. Yeah, that's right. So you can cache this, yeah.
And then you can compare at every single time step is this the minimum or this value that we just computed is the minimum.
Yeah, and you can cache this. You can cache this.
And then you can take the discretized difference just divided by the step, and then that will be your gradient.
I don't know what you mean by that one. So what you'll do is like, you'll take this guy. You have to actually compute this every time, but you can cache these two and this for every trajectory time step within a trajectory. And then at most 80 times you'll run over those, so you reuse them 80 times. But each one of those 80 times, you're going to do this. So then you compare them. If this one's bigger, good, then you do the gradient of this guy. And then update.
Like if you, let's say, write a function here, minimum of x squared minus 1 and value, value of x, minimum of x squared minus 1, value of x.
Okay. So that's going to look like, what is it, x squared minus 1, this.
And then, so the way we would do that is, we can assume that we already know this value. Like value could be thought of as that, the pre-computed one.
Yeah.
For each iteration.
Right.
And then you can here, let's say we're starting from left to right in this axis or x-axis, and you will see is x squared minus 1 smaller than this or not. And then if it is, then in the gradient, when you will have to compute the gradient, you will just take the x squared minus 1 and subtract it from the last.
Are you calculating gradient that way?
Yeah.
It doesn't work. Because the gradient has nothing to do with all these functions. The gradient is purely the derivative of this guy with respect to theta, which doesn't care about all this stuff. So nothing about caching any of this will give you any advantage when computing the gradient. It's a totally separate calculation every time.
How would you do it? Not that.
You take... Okay, so this, I think this is what you were asking earlier about reinforce, actually. So what this is you want to know what the gradient of theta, so the gradient with respect to theta, of theta, pi sub theta, at given st is. Okay. So it is like a Jacobian, sort of. So your theta is a big vector. So this will be a, is it 2D? Yeah, because it's not quite. The pi is going to be a vector. The theta is going to be a vector. And so if you differentiate a vector value function with respect to a vector value function, it is a Jacobian. You get a matrix. So this will be a big matrix when you do this gradient. Is that right?
Or you can just pick one of the elements in that vector and just, instead of taking it all at once.
This won't be a Jacobian. This should be a vector.
It has to be a vector because you're descending us
Right.
in that
That's
direction.
what I'm thinking. So why do I get something funny? So let's look at the pieces. AT given ST. So this is like what the neural network spits out when you plug in a state and action. All right. Here's the problem with that. This is a vector. This is not a vector. This is a number. One of the probabilities in the vector. And so this is the gradient of a scalar with respect to a vector. And so that's a vector, a row vector. Yeah, if you have like f x vector, and this is scalar, derivative is going to be a row vector. Yeah, so you just calculate that by knowing what your neural network design is and doing the back propagation calculation.
And for example, if the state is a two-dimensional vector, and if action is, for example, one-dimensional,
The state will always be one-dimensional.
state will
Oh,
no.
I take that back. I'm reading what you're saying wrong. I was thinking tensors, like the shape would be different. So yeah, you're saying a vector with two components for the state, and an action is a one component. Okay, that works.
And then let's say we have some distribution for that, like in a three-dimensional surface.
Like a policy distribution. So it's a mapping from states to actions. So yeah, it should be 3D.
And it could be a single surface. Like,
It will be. Yeah.
and in that distribution, so that would be a discrete distribution, right? Since that is being calculated by the trajectories we solved.
Those are samples of the continuous distribution.
How
It
is
can.
that continuous?
Sorry.
How is that continuous?
Okay, so you're saying you got a two-dimensional state vector. So S T lies in R2, and we assume it can be anything.
Yeah.
AT lies in R. Okay, so what you're saying is, all right, let's look at the probability distribution. Pi sub theta of AT given ST. So this doesn't exactly work. Yeah, this does not exactly work because this needs to be just a single number. This should be like Z2. So let's say 0, 1. So like, let's say you can do two actions. What you would want to draw, it's like just the distribution for A1 because I have to add up the one. Or sorry, I should say AT equals 0 given ST. So if you know the distribution for AT equals 0, you also know the distribution for AT equals 1. Just take 1 minus whatever the distribution is. Then you have that as the vertical axis, and your states are the horizontal axes. And so you get a surface then. And it's just between 0 and 1 for height everywhere.
But this still is not continuous.
This is a continuous distribution.
I mean, how would you find this out?
You don't ever. I mean, you can calculate it explicitly because you know the design of your neural network that takes you from parameters to probabilities. Just because you designed it yourself, it's like linear transformations followed by ReLUs, and then a softmax at the end. And you know the weights because you can inspect them in your memory, and you can calculate by hand what the distribution is and plot it. And people do this actually. If you see like people looking at loss distributions and how they look, they're doing this, and then some extra steps. This doesn't work if your actions can be like real valued, because then instead of having just one axis for two values, if you had three values you could take actions, like 3 actions you could take, you would need 2 action axes. If you have real number for actions, you have to have infinitely many axes for your actions. So it sucks. It's better to view it as a fiber bundle where you have like, imagine this axis is not the probabilities anymore, but instead it's the action you take. So this is AT. Then you have your state axes. ST. So then you can imagine there's a probability assigned to every point in this space. So the whole 3D space, you can look at a single point and check what the probability is there.
You can do this by like color dots to visualize.
Well, it's going to be 3D voluminous. So you can do contours, but it's going to be topologically, it's going to be 0, 1 cross R3. So it's a interval bundle over the real 3 space. Yeah. Yeah, in general, this is going to be your action space across your state space, across the probability space. Yeah, so that's what noise is. An interval bundle over the product of your action state spaces.
Now we're even gonna look at like how they actually implemented this in code. Will be interesting. Like the weights update step. Like I wanna see like how it is actually implemented in the code.
So this is gonna look almost exactly like we did with the reinforce. So there's Julia code in my repo for it, but I am gonna not write my own PPO. I'm gonna use the OpenAI baselines version, unless I do Julia, in which case I'll probably. I think VJ is gonna write his own in Python. But yeah, you can check the baselines code to see how they do it. Because there's going to be some stuff that's kind of tricky. Mostly not too bad. And double check that this is correct by looking at this generalized advantage estimate paper. But this should get good policies pretty quick.
You think having the what's it called, the lambda?
Hang on one second. Might be able to hear your question.
What was the lambda again? I forgot the name of the lambda. Yeah, the discount. So you took away the discount from RT here, right? This.
No, I put it in the calculation. So I just said, instead of just taking the sum, like I wrote down earlier with the RT equals the sum of all the remaining little RTs, do something like this. So the notation they use in the GAE paper is this. So I'll just write. I can't use tau, so
is it lambda to the square, lambda to the I times the reward?
No, I don't want to use I because that's for different trajectories. I've used up all my letters. Let's use J.
Yeah, okay.
So it starts at T and goes to big T, the end of the episode.
Yeah.
And it's going to be lambda J. Yeah, you're right. I think this is it.
Yeah.
I think. And the default that they use is lambda equals 0.97. Like that. I don't know. I think it's probably they want to kill off 0.03 every time. And like typically, because like if you're looking for numbers and you don't know what order of magnitude they need to be, and the order of magnitude is what matters, and not the like cutting it in half or like multiplying it by 3 or something. Like if you're not looking for a magnitude of a number, but instead of an order of magnitude, you're looking for, then if you started at 1 and it's too big, what do you go to then? You might go to 0.1. Well, what if that's too small? Well, you probably want to go to 0.5, right? This is wrong. You shouldn't do this. You should use 0.3. It's probably the fact that 0.03 is getting killed. So that's
I'll just take a picture of it.
Let me section the top off. And I sent another picture of a slightly cleaned up version that has some other details. So I wonder how you do this online. So if we had a rocket and we wanted to learn while it's flying, what would we do?
The only option I can see is like do not throw away your trajectories from previous steps.
The issue is the trajectories. You want to learn during a flight, so how do you get a whole trajectory, you know? Because one trajectory is a flight. So, I'm thinking you could probably chop the trajectory, like take parts of it, because you have a value function.
I think you have to do something like control horizon. You have to define that, hey, let's have this as a control horizon.
Right.
And if you know that, then you can simulate in advance what's going to happen.
So you can't do simulation, and definitely not on a rocket controller. I think it's too expensive.
Now, physically we cannot, but like ideally.
Yeah. But I think what people do in practice, because this is supposed to be a model-free method, no simulation whatsoever. I think what I would do as a first attempt would be to just chop the trajectories early and not go until the rocket hits the ground or whatever, and just say, all right, I'm going to start saving trajectories. I'm going to go for the first 5,000 time steps. I'm going to stop there, and that's going to be a trajectory. And how do I know if I did good or not? Well, I have this value function that worked from earlier. And so it tells me if I did good because I've trained it to know if I did good or not, even though I haven't finished the episode. Right. So you do have that online coming from the online training coming from the value function. And then, you can just compute your rewards from that. And you just won't update your value function anymore until you get true rewards. So you actually can. You can keep training your value function.
Also, the second question. Let's say you're going from this simulation to like real, and let's say the refresh rate is not the same. Do you think it's going to be a problem?
Yeah. How much of a problem, I don't know, but it will be.
And why that?
It's just not what you trained on. So you want to...
It's just interpolation that is happening. Let's say the refresh rate on the actual rocket is higher than this, and we would want to do that because this will.
No, you can help. Like you can help it, but firstly, if in the sim to real, like the real case, if you're getting a low refresh rate, which is the issue you're worried about, if you're getting a low refresh rate, then you're saying do some interpolation to get extra steps.
Oh no. That's not what I'm saying. Let's say this was run on a 30 hertz refresh rate, whereas the actual rocket is running on, let's say, 120 hertz refresh rate.
Yes. That's good. You can accommodate for that.
But it can transfer over, right?
Yeah, you just chop it. Like you sample it more sparsely. That's
right.
Refresh rate.
Simple.
But yeah, you want to control for your sample frequency for sure. But you don't want to use a different sample frequency that you just turn it.
Why do you think it's going to be a problem?
Imagine I took your vision and I 60x'd the number of frames you experience and kept the frame rate the same for you, and then you tried to play basketball. Like, you would not be able to react with these. I mean, you would be faster than them, but that's just because you can reason and stuff. Just makes it easier. Actually, if you're not using recurrent networks, maybe it's fine. I think stability is going to be a problem. Like, you might have oscillations, hysteresis, kind of thing.
I think it can lead to oscillations. Okay, so
it might not be a problem. It's certainly better to go that way than to get to small refresh rate.
The reason I asked the question is if we can cut down the refresh rate on this, it's gonna save us a lot.
Yeah. Just train it as low as you can tolerate. Your procedure for developing this for the actual rockets control is going to be, hey, go on to, figure out what the chip's going to be on this one. Try some neural network architectures. Run it in the real world, plugging in true sensor data, and then, or whatever your estimations of this data. Run all your other software at the same time. And then try a certain neural network size and see how you get performance. And if it's getting a good enough refresh rate, you're fine. So you figure out your parameter size from that. And you can just decide then what you want your refresh refresh rate to be. And then you need to train in the simulation with the same refresh rate. But you want it to be stable and there be no spikes or flags or anything.
And you think the same architecture, like all the same similar hyperparameters, let's say we're just like doing like initial stage training just to get the idea if it is converging quickly or not. Like we don't want to train for like a billion episodes, right? So let's say we just want to make sure it is converging within like 100,000s.
Yeah.
And we ran at like 30 hertz. Do you think it's gonna make sense to use similar hyperparameters and like do the actual training for, let's say, 120 hertz?
It will be more expensive. For hyperparameters, I don't think anything's going to change too much. Because you're still just doing one of these per episode. Or per batch.
You might want to change your clipping factor.
No, because it's per time step. You're right. It's true. You might want to because it is per time step. But I think the clipping factor is kind of, you don't really have to tweak that much in general. Just because you're using Atom, which is adaptive. So I think Atom actually gives you a lot of benefit in that you don't have to tune your hyperparameters too hard. I noticed this with Reinforce, like I just used my tried and true 3E -4 and it worked perfectly. I didn't have to tune it at all.
It also depends upon like how much of a difference you're doing. Like if from 30 hertz to 120, like you're cutting down time step by 1/4. Yeah. So your sensitivity is like a lot higher.
Yeah.
You would want to probably reduce it by half or something. Not sure.
It's tough to say. I mean, they have one default value, which is 0.05. Or maybe it's 0.01, I can't remember, for this epsilon clipping factor, but they don't suggest that you really have to do much tuning of it. It's like just plug and play. I don't really think you're going to have to change your parameters here that much. Because you're going to average over your time steps anyway.
That's true, but for if so, you're averaging the values after taking the minimum, right? But if your minimum is getting affected by that, then all the values in the average will be affected, and the average will also be affected.
So your states are not changing much from one time step to the next. They are over the course of the episode, but with reasonable refresh rate, they're not going to change that much. So the values inside the minimum are not going to change too much. So mostly you can expect them to 4x if you go from 30 to 20. Like you'll just get 4 perturbations of the original values. It'll matter if these are really close the whole time and you keep oscillating between. Because then you'll get sporadic number of updates of this. Because if you hit this, you do update. If you hit this, you don't update.
You're right.
But you want that not to happen anyway.
You're right, because like T will also increase.
Yeah.
The capital G.
Get a 4x.
So it will probably account for it.
Yeah, as long as you don't have weird oscillatory behavior with this is like switching back and forth between time steps a lot, you should be, like it literally should behave the same way. It should be more expensive to train.
I'm gonna have to go now. My class started 18 minutes ago.
Alright, I'm gonna end the recording.
Is there anything other than PPO-Clip that we discussed?
I want to look at GRPO eventually.
It literally looks like this.
Yeah, it should be small. Just some slight change to that big rule. GRPO. There's also stuff like DQNs and rainbow networks or rainbow training. Mu0 for learned models. That'd be pretty cool. But if
One done
PPO,
by Google,
yeah, there's like, so the model-based methods that I like, I don't want to make one that you have to program a model for. It really sucks because you have to run a simulator. What you can do is you can make the neural network have a third. You can have a third neural network that learns to come up with latent embedded representations of the world state, and it'll evolve it in time for you. And there are two main algorithms for that. The first one's called Mu0, and this was used to play Go.
I think you sent me a paper about it.
Yeah, this is the one that made me want to do a math PhD. But there's another one that came out more recently called Dreamer V3.
Okay.
And that one you can actually visualize. It's not as latent, like as abstract world representation, but you can visualize what it's seeing as dreams, so to speak. Pretty cool. Yeah.